Welcome back. We're going to continue our week 3 discussion on bonding, okay, and how bonding affects a molecule's polarity. That is, how can bonding affect a molecule to be, polar covalent, okay, ionic, or it's non-polar covalent. Okay, so these are the three types of compounds that we learned, and in addition we also have transition metal compounds, which are also kind of ionic in sense, and then we had the covalent or nonpolar. This is, I'm just going to write aka covalent. Okay, they are essentially the same thing. All right, and then we learn how to do electronegativity values to classify them. Okay, classifying is one thing, but actually understanding bonding is another thing. Okay, and I mentioned that bonding has a lot to do with the Roman numerals. The Roman numerals is an indication of how many valence electrons you have, right? Let me bring up the periodic table. Okay, and if you notice, that's 2a for beryllium. That means beryllium's got 2 valence electrons. Let's say we go to carbon, and then we say that it's got 4 valence electrons, nitrogen's got 5, etc., right? Good. Now let's come back and discuss, before we go to bonding, there's 2 types of electrons you need to know. The first one is bonding electrons. Okay, you can guess from its name, it's involved in the bonding process. Okay, involved in bonding, that is, they're part of the bond itself. And then there is non-bonding electrons. Okay, you need both to really be, and some molecules only have bonding electrons, some molecules have both bonding and non-bonding electrons. These are also known as lone pair of electrons. Okay, lone pair of electrons. Okay, because I want to get you familiar with this terminology before we go further in the concept. Okay, so now let's go actually build a compound. Okay, let's get a compound. I think you are familiar, since you have just done the naming compounds, you probably have done this compound. We've named it. If you have still not got it right, well, I told you that you need to know that chlorine becomes chloride, right? And there's 5 of them, and phosphorus. So whichever element is first in the list is named first. So it's phosphorus for P, pentachloride, right? 5 chlorines, so it's pentachloride. This was the first thing we learned in week 1, right? We learned how to name compounds, phosphorus pentachloride. Now if you go back to the periodic table, the Roman numeral for phosphorus is 5a, and the chlorine is 7a. Okay, right? Very good. That means this actually has 5 valence electrons. Okay, 5 valence electrons, right? You even did this on homework too. This has 7 valence electrons. Well, valence electrons are the ones that are actually available for bonding or non-bonding. Okay, not the total number of electrons that an element has. Okay, so before we learn how to name a molecule, like the geometry and stuff, for now you always put the element that's the least of the 2 in the center. So this is the least because this is 1, there's 5. So you put the phosphorus at the center. Okay, and then it's got 5 valence electrons, so I'm going to be consistent. Just put them anywhere you like. Okay, just put them around in a circle or some form that all 5 electrons around the chlorine, right? Good. Now chlorine has 7 valence electrons. Okay, now the easiest way to tackle this understanding of this whole concept is, chlorine has 7, right? Split them into pairs of 2. Okay, split 7 electrons. You should do this for all elements that are on the outer side. Okay, elements that go on the outside, not in the center, you always split the 7 electrons, split whatever many electrons you have into pair of 2. Okay, right? Pairs of 2. So what does that mean? Let's go get our red. So that means chlorine has 7 electrons. So if I split it in pairs, okay, and then I'm going to get 1 electron that's not paired, right? And there's 5 of them, so you have 5 like this, okay. I'm only drawing it for 1, but then you have 5. So split the 7 electrons into pair of 2. Well, I can make 3 pairs, but then there's an odd electron that's left out. So what I'm going to do is come back and write it exactly the way I have it there, okay. So I have 3 pairs and an electron. So do that for all 5 chlorines. So pairs of 2, okay. I'm teaching it to you in a more simpler way, because otherwise this concept can get out of hand and can cause confusion and chaos. Why are you doing it this way? Because the fundamental theory is there's 2 electrons in a bond. Okay, just because you have 7 electrons, you cannot have 1 and 7 electron bond. It is always 2 electrons in a bond, right? Now let's go get a different color, maybe a black. Now it's simple, right? These are your non-bonding electrons, okay, or I'm going to call them, these are your lone pairs, okay. They're not involved in the bonding itself, okay, but they're there, okay. But the element can just take 1 out of the 7 and go pair with the phosphorus. It has to take the lone pair with it, okay. But they're not involved in bonding, as you would see here. I'm only connecting that odd electron from chlorine to the odd electron from each of the phosphorus, each electron on the phosphorus, right. That's how phosphorus would bond with the Cl. Now we learned PCl5 is a covalent compound. Why? Because it's a phosphorus is a nonmetal, phosphorus is a nonmetal, chlorine is a nonmetal. So we would also learn down the road that polar covalent compounds also contain 2 nonmetals, but they're polar covalent because of that electronegativity difference. I will come back and do it. So let's go get the electronegativity value of phosphorus. Okay, phosphorus is 2.1 and chlorine is 3.0, right? Okay. Okay, phosphorus is 2.1 and chlorine is 2.0, sorry 3.0, right? So the electronegativity difference is 3.0 minus 2.1, right? It is 0.9, right? So it is technically polar covalent, okay? Okay, it is, the bond is polar covalent. Now this is what the electronegativity table does not tell you, okay? It's 0.9, right? So there is, the whole molecule itself is not polar covalent. It's just the bond is polar covalent, right? So let's understand that. So since it's polar covalent, right, we primarily use this concept not to classify the compound itself, because there are exceptions. Sometimes the values themselves match with the compound, but sometimes they don't. But this is primarily to assign charges, right? Of the 2, phosphorus is small, chlorine is 3. Remember I said when it's between 0.6 and 1.6, I said it's polar covalent, right? That means we use partial charges. So I told you you can use this or this, whichever one you feel comfortable using. For the convenience of it right now, I'm just going to use, so chlorine is more electronegative, so that gets the tail, and then chlorine, again in all these cases the chlorine gets the head and the phosphorus gets the tail. So this is how you complete the bonding process, okay. So the bonds themselves are polar covalent, but I can tell you as a whole this molecule is nonpolar. Okay, the molecule is nonpolar. We'll get to that in another video. I do want you to understand, that is why I'm saying this, is the molecule itself is nonpolar. That means if I put this compound in water, it would not be soluble. But this charge separation, the electronegativity differences we did, is primarily to assign charges, positive or negative, right? So, and then similarly when we did sodium chloride, we gave full positive, full negative for nonpolar covalent or purely covalent, aka covalent. We didn't give any charge at all, right? So this electronegativity difference is primarily to assign charges like this, or if we should assign charges or not. But you would learn down the road, despite the fact the molecule contains polar covalent bonds, the overall molecule is nonpolar. Okay, that's why I said the electronegativity table does not answer every question about molecule polarity. Okay, it only tells you whether the bond is ionic, whether the bond is polar covalent, whether the bond is nonpolar covalent, aka covalent. But it doesn't tell you about the overall polarity of the molecule. I'm telling you this molecule is nonpolar, which we will come back later, okay, when we actually learn via CPR theory that why the molecule is nonpolar despite the fact it's got some polar covalent bonds in it. Okay, that has to do with the geometry of the molecule. That's what via CPR gets us into, and I don't think we are quite there yet. Okay, so but for now I just want you to construct a couple of molecules. So let me give you, let's do one more, okay, NH3. Okay, and if you notice, nitrogen has got 5 valence electrons, so it's 5a, and hydrogen is 1a. Now that is for one hydrogen, you have to do it times 3. So this has 5 valence electrons and this has 1 valence electrons, okay, times 3 because there's 3 hydrogens, right? All right, now let's go get a different color. So let's get nitrogen, and okay, sorry, this is not quite getting the blue, so let's get the nitrogen. Okay, as I said, it's got 5 valence electrons. Put them wherever you like, but don't put them anywhere on your paper. Just put them somewhere around nitrogen. And each hydrogen has only one, so you don't even need, you cannot even split it into pairs. Okay, you only split it into pairs when there is more than 2. Okay, because 2 itself makes a pair. Okay, which we will also learn. Only when you have really more than 2 electrons, like 3, 4, 5, 6, 7, 8, 9, 10, you divide it into pairs of 2. Okay, that's why helium cannot bond in the situation, because it already has a pair. It does not have that extra electron. Does that make sense? Okay, so hydrogen is 1 and you got 3 of these, right? So let's get a different color for hydrogen. So you got the hydrogen, doesn't matter which one you attach to. Some people get too obsessed about it. Don't get obsessed about it. Just put them anywhere you like. Okay, just you can attach it to the top 3, bottom 3, or any of this 3 or this 3. It really doesn't matter. They all have the equal probability of. So I'm going to get my bond, right? So now if you see, there's 2 electrons left, right? There's 1 here and 1 here, right? So let's rewrite this molecule. Okay, let's get. So what I'm going to do is, I'm going to put, they're technically separated, but we're going to bring them together. So what I'm going to do is, I'm going to bring the 2 odd electrons that are far away and put them as a pair, because that's a lone pair, right? Right? I usually put lone pairs are put inside an oval. So what I did is, the ones that are not involved in bonding, I collected them, put them in the same place, and then I put the 3 hydrogens. Okay, right? Very good. Now let's go get, this is how you bond, right? So there's 2 electrons for each bond. Okay, but we're not done yet. We have to assign the charge, right? So, if you go to the electronegativity table, nitrogen is 3.0 and hydrogen is 2.1, right? Nitrogen is 3.0 and hydrogen is 2.1, right? So, 3.0 minus 2.1 is 0.9. That means it is polar covalent. The bonds are polar covalent, right? That means nitrogen is 3, hydrogen is 1. So, nitrogen gets the arrow, the head, and then hydrogen gets the tail. Similarly, let me, if you guys want, I'll just do it in a different color so you can see it. It's all blue over here. Okay, so let's get a pink. Okay, so the nitrogen gets the arrow, hydrogen gets the tail, nitrogen gets the arrow, hydrogen gets the tail, nitrogen gets the arrow, hydrogen gets. Let me remind you all, we're not saying about the molecule's polarity, we're only talking about the bond polarity. Okay, I can tell you the molecule is polar. Okay, but we will learn this again. We haven't learned geometry, but all we're assigning here is bond polarity. The bond, this is polar covalent. And how do I know that bond is polar covalent? Based on this value right here, because that's between what, 0.6 and 1.6, right? That's polar covalent, right? Anything above 1.6 is ionic, right? So, I want you to practice these. Okay, so let's say I'll give you these compounds to practice: XCF4, BeCl2, MgC. Sorry, I don't think Mg would work because let's do this. LiCl, and like I said, when you're constructing the structure, the molecule that's the least goes in the center, the one that is more goes on the outside. Okay, pH3. Okay, practice these 4 compounds. Okay, draw structures like I did. Okay, and assign polarity. Okay, only if it is, assign polarity if it is polar covalent or ionic. I don't think you can do polarity for covalent. All right, so that's your homework, and when I come back in the next video, since this is also happening in class, I would rather hang on to it and do this in class, but then later I will post at some point a solution to these 4 problems as a separate video. Okay, all right, stay tuned for the next concept on this line.